Last spring, I was preparing a talk for the Health Physics Society, the organization I'm a member of, a technical talk, and I thought it'd be a catchy title to call it The Dirty Bomb. And it was. The talk went off very well. It had about 8 slides, very dense with numbers and graphs. And when the title came up, people thought, wow, this would be a great talk. And they said, would you come and give it? So I said, yes. How long do you want me to talk? And they said, as long as you like. And we have the room to midnight. But actually not. I said, well, I could talk for an hour. And I could try to appeal both to students, researchers, if there's any, and the general public. It's a hard row to hoe. I gave an abstract similar to what I had given for the professional meeting. The Trinity test in '45 was actually something that might occur with a dirty bomb. A small fraction of the plutonium was used in the explosion, detonated at low altitude. The fireball contacted the soil, and it resulted in extensive fallout downwind, although very little fallout near the test site. And although there were plans for evacuation didn't occur. And so I want to talk about that today. I guess I'll first do a couple of cheat slides on my presentation, the title. When I gave it, of course, all the technical experts said, well, technically a dirty bomb is a dispersal device where you just take radioactive material and blow it up in a city. And Trinity clearly wasn't a dirty bomb. And I said, okay, what should I call it? They said, well, it wasn't really an improvised nuclear device either. And so they told me that I shouldn't use that title either, but I like my title, so I'm going with a dirty bomb. And I hope you understand more as I talk about it. 4 things last spring caused me to give the paper and the subsequent talks, and I'm very grateful UNM invited me to talk here. I was asked to chair the session on dose reconstruction at my professional meeting. Dose reconstruction is where people like myself give papers on if there were releases from a facility, how to calculate the radiation exposures to members of the public. So it's a very interesting area for me personally, and I was asked to be chair, and I felt I ought to give a paper at my own session. And afterwards, 3 things happened that I thought were kind of interesting. I was asked to review a paper submitted to the journal, Health Physics Journal, by Los Alamos on the plutonium from the Trinity device. And the paper, I'll get into it in the next slide, was quite fascinating, but was more fascinating. There's apparently a complement of about 6 papers being written for the journal that they had submitted to be, and I was asked to be a reviewer of one of the reviewers of one. And there was another scientist, Bob Alvarez, contacted me and discussed his work and his wife's work on the Trinity project, and that struck my interest as well. And the best man at my wedding became eligible for the Energy Employee Act. And so these were all coming together in a way that said, well, I ought to talk about Trinity again. And so let me first talk about the second reason, the Los Alamos paper. In chapter 10, I noted that 80% of the plutonium wasn't fissioned. The Trinity device had a solid sphere of plutonium metal that was crushed by explosives, right? And if you just look at the unclassified number in Wikipedia and other places, it had about 13 pounds or little over 6 kilograms. And there's also amount of energy released when a single atom of plutonium fissions. So you could take those numbers and you could say, well, how much of the plutonium fissioned when the weapon was set off? And it turned out to be 80%. I was really surprised at it. I had done work on shipping work for more modern devices, and I was quite surprised at plutonium. But the paper that they sent me for review pointed out I was wrong, and I hate being wrong. But it pointed out that it's really 85% because many of the fissions that occurred in what was called a tamper. To really crush the plutonium uniformly and very quickly, they surrounded it with uranium. And when the crushing occurred, the uranium helped keep the plutonium from squirting out. You could try to think of squeezing a balloon or something. And the external shell of uranium kept it all together, but it also provided more fissions as the neutrons from the plutonium hit the uranium and caused it to fission. So I was wrong. They were right. I thought it was a good paper, and I thought it should be said. Both the Los Alamos paper and my own ignored the contributions from other what are called transuranic radionuclides, TRU, notably the plutonium-240 and 241, that were present in the Trinity device. They minimized it, but when you create plutonium in a reactor, you create other forms of plutonium that are detrimental to the operation of a plutonium bomb, but they're actually quite effective at giving dose to people. They're plutonium. And so if you consider the actual fact of the other two nuclides, it increases the dose from inhalation from plutonium by more than 2/3, which, as an engineer, that's a big change. So when you look at it, normally if you're in a plume of fallout from an attack on a city with a nuclear weapon, you'd be concerned about things like inhalation of strontium. And the plutonium from these early devices was more important than the strontium, which I don't know how many of you find that fascinating, but I did. Alvarez and his wife, now deceased, worked in Hazel O'Leary's office in the 90s. They had a project called the Human Radiation Experiments, where the Department of Energy was attempting to find all work that they had done and identify that work and make it public just so that they would respond to any concerns. There was a famous incident. Oak Ridge, during the time the bomb was being developed here, was also very actively engaged making radioactive lanthanum, the rallow used in Los Alamos. And unfortunately, a black truck driver had a serious truck accident just outside of Oak Ridge. And he was taken by emergency services to the hospital. They thought the fellow was going to die. And so they thought, he's going to die, let's inject him with plutonium and see what happens. And they actually did that, and the guy got up and walked out. It was kind of startling. So that's an example of an experiment. In fact, when I went through records looking for this type of material, it was very interesting. By 48, we had the World War II Nuremberg trials. And it began to establish what is legal and illegal for a medical doctor to do to a patient. And there was a criteria. The Nuremberg criteria became present in all the doctors of that era, and it has subsequently led to the development of those many forms. If you go into a hospital today, you sign 15 forms with fine print, warning you it could kill you, telling you your rights, and so on. But those type of experiments caused concerns. All of that information was released, and Tucker was intrigued by correspondence from the 40s in which New Mexico-based doctors questioned whether spiking in infant mortality that following the Trinity event could be related to the fallout. And that was a startling paper for me to read because I was familiar with Trinity and I was unaware of that work. The response from the Manton Engineering District was, no, it wasn't a problem. However, the data wasn't requested from the state of New Mexico for some months later. So it was just a pro forma response. It wasn't a problem. And they only began to look at it somewhat later. One of my problems, so I called CDC after I saw that paper immediately saying, you know, that you ought to look into it. We never saw that paper. We were provided unrestricted access virtually to Los Alamos. Either we were asleep at the switch and missed those sorts of documents, or those documents weren't made available to us. So I was concerned about that. That's the third reason. The fourth, this is the graph he showed. There's a group called Federation of American Scientists formed in '48 to try to warn people about nuclear war. And they have a monthly publication, the Bulletin of Atomic Scientists, that has a very famous clock. It says, how many minutes before midnight are we, reflecting how much in danger the world is for a global nuclear war. And when they move the clock forward a couple of minutes, it makes the news, or when they move it back a few minutes, it makes the news. They have a publication, and that's where Alvarez published he and his wife's work. This paper's from that. And if you look in the months, good, I'm not hooked up. In the months, I'm not wired. I'm wired always to Sunday, but I can walk. But I don't have a laser pointer. But if you look, in the period immediately following Trinity in '45, there was a spiking in neonatal deaths for a variety of causes. Now, those deaths since the 30s really have generally been declining as medical practice has improved and infant mortality has been dropping even till today. But any spiking like this is very provocative. Was that an impact of the weapon or not? And I think it'd be, if you were a nursing student here, it'd be a fascinating project to try to look at independently. You'd come across a lot of detail that would be relevant to your own work, epidemiology and others. Now, my best man, I have to say, I think when I was in high school, they sent 2 guys around, Meyer and Briggs, to give us tests to see what we'd be good at doing. And so the guidance counselor had me take this test, and I flunked it. And they looked at me and they said, the only thing you are capable of doing is engineering. Don't try anything else. So I'm the only person I know that flunked the Meyer-Briggs personality test. But normally it says if you're touchy-feely and all this other stuff, and I blew that off in high school. But I married the opposite, and my best man had sent a number of emails, and she said, you ought to quit what you're doing and go see him. And last spring I dropped things and drove up to Oak Ridge, and I found out that he was eligible for it. I had stopped at a restaurant we frequented when we were in Oak Ridge, bought Chinese food, takeout. When I arrived at his house, his driveway was full, and I didn't know what was going on. And I walked up, and he is gravely ill, he's ill, not hospitalized. But when I walked in, he had 3 medical professionals attending him. And so I stood back, and as I found out, one was a physical therapist trying to help him maintain his strength. She'd come 3 times a week to do physical therapy sessions in his home. Another was a home health care provider working with catheters and other pieces of plumbing that I don't want to think about. And the other one was some sort of coordinator person. And so I waited till they left, and we got to talking, and he said that he qualified, he was eligible for the Energy Employee Act. It's a very generous program. They provided him a walk-in tub, and as they're getting older, it might be nice, they provided him a stair climber. And he wasn't willing yet to take one of those personal mobility vehicles because he thought that was another step towards the grave, and he wanted to fight it. But he said, do you know when you went to the restaurant, get that Chinese takeout we're eating? And I said, yeah. And he said, do you see the office building opposite? And there was I said, sort of, you don't really pay attention to things. And he said, it's a 5-story building. They've got a group in there who's paid to help people apply for the Energy Employee Act. They got another group in there, that's the nursing company that provides home health care nursing, so that he doesn't have to go to a nursing home. In his condition, he might either be in rehab of some form or nursing. And there's a Department of Labor that runs the program, NIOSH that calculates doses for impact, the Department of Energy. They all have a role in that. It's a massive program. I don't object to it at all, but it's an extraordinarily generous program to compensate workers. And as that program goes, this describes the program. So if you're a worker, you can either be designated a special exposure cohort, and what this means is we knew so little about their exposure, and they were such a powerful union, perhaps, that they were just granted compensation if they had a radiosensitive cancer, one of the 20 or so cancers that we know are more sensitive to radiation. If not, if you worked there and had a cancer, then NIOSH would calculate your radiation dose and determine whether the cancer is at least as likely as not. Now, what's that mean? I love math. Okay, everybody ready? This is the normal probability distribution table. I'm sure you probably have heard it, the bell-shaped curve. And it's plotted in a little different way. I've plotted it in standard deviations. So normally if you go to Home Depot, and standard deviations aren't the numbers of it, it's the probability of things. Between one standard deviation on either side, 2/3 of the numbers occur. So let me put it practically. You go to Home Depot and you buy a box of screws. There's 100 screws in the box. And you put them on a very sensitive scale and measure each screw. They're all going to be about the same. If you put the weight, it'd be a very, very narrow peak, but there would be one screw in that box that was the lightest screw, and one screw that was the heaviest. That one screw would be 3 standard deviations out. That's how we use this curve. Now, if there was 100 people in this room and we all got on a sensitive scale and measured our weight, I'm not proposing it tonight, there would probably be some of you who are extremely light, and the lightest person in here would be there, and others, and I'm not pointing fingers at anybody, but others might be here at the 1% level. That's what 1% means. What does the DOE Energy Employee Act mean, at least as likely as not? Well, Congress told us when we were calculating it, do not unfairly deny a person compensation. And that was defined by Congress to be this 1% number. So instead of, if you had a cancer and you had an exposure several years before, and the probability that it caused it might have been a certain value. That would be the value you might think, okay, if you get 10 units of radiation and that's what would cause the cancer, you ought to be compensated. Well, we can't measure that 10 accurately. And so if you did it exactly at 10, there may be workers who got 10 but were measured at 9.8, or other workers that got 12 and maybe had a low number below 10. How do you separate those? So what Congress told us was go 3 standard deviations out, which for a normal distribution is a large number. It's to the 1% level. Now, that's how Department of Energy workers are awarded compensation, at least as likely as not. Now, let me go one more step, and that is, what about a worker who only got, if it was 10 units, you get compensated, 5 units you don't, right? Well, if you got 5 units, you shouldn't be compensated, should you? You would think. But 5 units might be a graph that would be a curve here, because some of the 5s would be high and 5s would be low. So you would end up compensating some of the 5s by accident because their numbers fell above this very low number that that Department of Labor and Congress required. So when we started the energy work, there's a massive project, a lot of years, a lot of people, and workers became able to apply for benefits. If you were a DOE worker and had cancer, you could apply for benefits. And they did. And we had what we called the backlog, because we weren't ready yet with all the calculational machinery to do the calculations. We had 38,000 people in the backlog when we started in 1990s. And we crunched through all those people as quickly as we could, and about 11,000 of them ended up compensated. And of that number, perhaps 100 would have been justifiably compensated at 10, but we had to, if we had set the number at 10, we would have missed 50 out of that 100, because 50 would have been lower and 50 would have been higher. So you would have missed it. You wouldn't have hit what Congress said. So we had to back that number down so low that 11,900 people who fell below 10 were compensated anyway. So the Energy Employee Act was an extraordinarily generous act by Congress to compensate nuclear weapons workers in the complex. And I thought that was interesting in that you can contrast it with the Radiation Exposure Act. Now, I worked on what I mentioned earlier in the introduction, the Los Alamos Historical Document Retrieval and Assessment Project. CDC about 20 years ago hired a group of scientists, including myself, to review all of the documents, get them declassified, scan them in, and to the extent we could, optical character recognize them, create a database for it. If you go up today to the Centers for Disease Control website, cdc.gov, and look on their website for La Hadra, you can get all of our reports. I believe you can get many of the documents we declassified from Los Alamos. And Chapter 10 of our final report, which was issued in 2010, deals with Trinity, and it summarizes everything we knew. The Trinity test was recognized to have a very significant impact from that study, and when we ended up about 10 years ago in 2010, CDC looked at it, and one of their sister agencies within HHS, the National Cancer Institute, had already done the Nevada test site studies and had already developed the machinery for the Utah downwinders and the downwinders impacted by testing there. And so the dose reconstruction was left to NCI to address. I believe the project manager is Steve Simon, and I spoke to him fairly recently, and he said, we're finally done with the report. It's going through all of the reviews and checks the government requires. It should be issued in the spring. So I think you'll find very interesting reading this spring when NCI finally releases its study. The project, we did not find the information on the Alvarez paper, the infant mortality data. So that La Hadra project was what I work at. That's why I'm here. That's why they asked me. But what made Trinity different from other tests like those in the Pacific and Nevada? One was the height of the burst. It was a 100-foot steel tower that it was placed on. A second thing was the distance to downwinders, where the downwinders in southern New Mexico were as close as 12 miles. And when they left the site, both Oppenheimer and Grove said, we can't do this again, we got to get a bigger site. And that was part of the selection of the Nevada test site, where the downwind populations were more than 100 miles away. Think of how fast the wind blows, 3, 4, 5 miles, 3, 4 miles an hour, 5 miles an hour. What's 100 miles get you? Well, 100 miles divided by 5 miles an hour is what, 20 hours? For a nuclear warhead, that's a lot of time for the decay from it. So in the case of Trinity, there was very heavy fallout, similar to the Baker shot at Crossroads, also a Trinity-type pit. The plutonium releases, as I mentioned in the start, were very large. There was iodine pathways, but the iodine pathways include very unique pathways. Given a rural area, groundwater's, well, I shouldn't talk out of school, but my impression is groundwater's unpalatable. It's highly mineralized. The college I went to had mineral water, I hated it. And so oftentimes they use cisterns to catch rainwater to get water that doesn't taste unpleasant for drinking and for cooking and other purposes. So many people had cisterns that would collect the fallout. The skin dose was extraordinarily high. And that also raises questions about the lens of the eye dose and infant mortality issues, as I said. So let me go on here. So this gives a picture, a map of the area from the Trinity site to where the dominant fallout pattern went, to the northeast. And in this map, you can see what 10 miles is and what 20 miles is. You can see the towns of White Store, Adobe, and Bingham are all within the 20-mile radius. There's also an area called Searchlight Station L8. This was where a group of the personnel from the test stationed themselves to photograph the plume as it went overhead. In initial planning, one of their thoughts was, there's so much heat and so much energy, the thing like a volcano would loft all the way into the stratosphere, and everything would be up in the stratosphere and disperse around the world in the stratosphere, like a hydrogen bomb would. And they had no experience, they didn't know whether that would occur, and so they thought there may not be a problem at all, it just may go away. The fallout may just go away. That proved to be wrong, but they did set up stations both to measure and to look at, and the searchlight stations had those spotlights you use at a automobile dealership when you're trying to sell cars. You put this big spotlight in and shine up, and the intent was, if the test occurred at dark conditions, you'd use a spotlight, light up the plume as it wafted overhead, and photograph it for scientific purposes. They also, on the searchlight team, put in radiation monitoring personnel. This shows this shows a little further distance out to 30 miles. You can see the location of ranches, farms, or camps in the yellow circles, and the green squares, this is from our report, are towns. There's, if it was a shotgun, you'd say you need to choke it down a bit unless you're going for ducks. But it has perhaps as many as 50 ranches. We don't believe this is all the ranches, because like Los Alamos, we use the USGS mapping systems and identified settlements from those maps. And even Los Alamos, after looking at those carefully and making all their plans for the Trinity test, were shocked to find settlements in the Hoot Owl or Hot Canyon area, sort of off to the upper right there in your view. This shows from the National Weather Service Support Office in 1987. They took all the data they had from all those searchlight crews and all the weather data they had to project what the fallout, what the radiation levels would be like downwind of the test, after the test. That was their intent. It's a nice figure. It tells us what the dose rates are. this 10 R per hour field is an extraordinarily high field. If you're working at a nuclear power plant, anything above 0.1 R per hour is under lock and key. It's called a high radiation area. So you do go in there under very controlled circumstances. You'll execute a plan, you'll make sure you got the right tools so you can quickly get the job done and get out. But that's a static, that always stays the same, where this was decaying fairly rapidly as the plume continued towards the northeast. So this is a figure, I may turn back to this later. This shows the figure at 12 hours. And you can see, well, it's dropped from down by a factor of 100 at 12 hours. This curve now is 100 millirem per hour. I don't have the scale on that, I'm sorry. And it was mapped based on the field measurements. It was limited by the primitive nature of the portable instruments. It was measured across the country. They found fallout from Trinity, for example, in Indiana, where Kodak had a manufacturing plant. And the film that was manufactured from that plant later darkened, and Kodak realized they had seen material that came from something. They had a scientist in Kodak that could realize that. And by 1948, he felt safe to publish it. He thought it might be classified. But Kodak ruined entire batches of film because of the fallout from Trinity. And unfissioned plutonium was not well measured until years later. So I love math, but I wanted to show, this is a very famous figure by Catherine Way and Eugene Wigner, the Nobel Prize winner. They were at Los Alamos. And in 1948 or 48, they looked at the rate at which fallout falls and came up with this relationship. It's been used ever since. And what it says, if you look at 1 hour, this line here, and you say, okay, if it's one radiation, if it's 10 R per hour, you'd put a 10 there. If it's 1 R per hour, you'd put a 1 there. If you look 7 times later, like 7 hours, it's down by about a factor of 10 to 0.1. And if you look at 7 times 7, 49 hours, call it 2 days, that's about here, it's down by a factor of 100. So every time you march out 7 in time, the radiation levels drop by 10. That's the power function they published in the Physical Review in 1948. And it's still used today. I mean, it's a very quick way to look at the decay of power in a reactor that's been running, and that sort of thing. So what's the difference between the Trinity Downwinders and the ones in Utah who have been the subject of the Radiation Exposure Compensation Act? So you've lived through all that math. Let me try to show a little bit more to show you why those two are different and what the differences is. And this is from the effects of nuclear weapons. And it's a hypothetical weapon set off, the same kind of weapon. In one case, we're dealing with the functions at 35 miles downwind, which would be similar to Trinity, Carrizozo, those kinds of places, 35 miles. And the lower curve, the curve on the right, is from 150 miles away, more comparable to what you saw in Utah, right? And what happens, you recall that curve, the fallout levels are dropping dramatically, very quickly. Every 7 in times, it's 7 hours, they're down by 10, right? And 49 hours or 2 days, they're down by 100. And so that extra 100 miles that Grove and Oppenheimer insisted they needed to have was very powerful in virtually eliminating the short-term dose. Now, this is the dose rate that one might encounter going up towards 100 R per hour and then decaying with that 7 and 10 rule. And this adds up, the dose of each hour adds up to show you what the total. So very quickly at Trinity, with the people in the direct fallout fields, those red areas in the 2 prior maps, had gotten a tremendous dose from gamma radiation, whereas in Utah,